I'm going to try to talk about some of the new therapies that have been approved and a little bit about some of the ones that we're still testing, and just try to explain, if I can, how we think some of them work, or at least how we think that some of them might work, because the reality is we don't really know totally how they work. These are the main things that I was going to talk about. Most of you will know quite a bit about Avonex, Betaferon, Rebif and Copaxone. And then the new things that have been approved in the last few years have been Tysabri, Fingolimod Cladribine was approved in January, Fingolimod approved in March this year, and we're going to wait and see whether a few more things get approved later on. Mitoxantrone has also been used in Australia quite extensively, and I've just put up here some of the situations where they've been tested. So we don't have a pointer, do we? No. Anyway, so CIS is sort of the clinically isolated syndrome situation, and you can see that Avonex, Betaferon, Rebif and Copaxone have all been tested in that situation. In the condition called relapsing remitting, which is sometimes a bit relapsing progressive, to be honest, those things have been tested. And Rebif and Betaferon in some situations have been tested in secondary progressive disease and have been found to work a little bit. Now, and then Tysabri, Fingolimod and Cladribine have been also tested, but none of them really yet in the clinically isolated syndrome situation. Because I wanted to explain a little bit how these things work, I just want to, there's slightly different slides to what Dr. Barnett and Dr. Booth have used, but I just want to talk a little bit about the immune system, because unless you know a little bit about it, you really can't sort of understand how the drugs work, I think. There's lots of different cells in the body that the white cells that the body makes. They make... and of those white cells, there's neutrophils which fight all the bacteria, pneumococcus, staphylococcus, streptococcus, and then there's all these other cells that used to originally be called irrelevant cells, actually. They were sort of discovered in Australia, partly by some people in... one of the people who won the Nobel Prize, but they're lymphocytes. They're small little round cells, and a lot of them come out of the thymus. Now, since then, we've got much better at actually divvying them all up into little categories, and they all wear little surface markers, or I suppose, a uniform with signs on them, fortunate for us, and to stop fighting, people gave them numbers rather than names, because originally they had all sorts of different names. The Cambridge group gave them Cambridge numbers and letters, and the Oxford group another group, and then they discovered they were all the same thing. So they've got numbers, and that's why they have numbers. And the CD actually stands for Classification Differentiale, because the French wanted a bit in there. So that's what CD stands for. And then the numbers are just the order in which they sort of got discovered and agreed about. And so lots of the most important ones are CD4 cells. They were the fourth one discovered, and that's quite an interesting cell, because it's that receptor is what the HIV virus binds to, so it turned out to be really important. And it describes the lymphocyte that sort of drives and controls everything. So CD4 cells are thought to be very important. The CD25 thing turned out to be also very interesting, and it divides the cells. You've either got the 25 on it or you haven't got it on it. And if you don't have it on it, you're really a very active inflammatory cell that does a lot of can do a lot of damage. It can rapidly reject a kidney, it can rapidly destroy a lot of brain tissue, it can do a lot of harm in rheumatoid, it can do a lot of harm. If you've got the CD25 on it, then you, in fact, are this regulating cell, which got discovered in Australia. And this cell seems to make the other cells behave, sort of like good policemen. So it's been interesting because Dr. Booth went over with you at just how many of the genes have been associated with these CD things. So some of them were associated with CD4 and some with there's a CD25 one that turns out to be important, and then some of the others have to do with all the other interactions. And quite a lot of the cells are probably working by changing exactly how some of these cells work. So if you just take all the negative cells, which are the cells that actually turn into various effector or action type cells, they got the main ones got Th1, Th2 and Th17. And they have the things in between them, which is the IL-4, the IL-6, they're the little molecules that talk between the cells. So some of the time the genes got found were the things that relate to the cytokines, which is the molecule that works in between it, and the other time the genes have been discovered that actually relate to what's actually defining the cell. Now, the other thing that's sort of worked out, that is finally we think we're working out, is that for every one of the nasty cells or the bad effector cells, you can actually make a regulating cell. And that's sort of proved to be very difficult, but in fact you end up with, if you've got nasty sort of, oh jeepers, now I've done it. If you've got nasty effector cells that are Th1 type cells, then you probably need a regulating cell that works against that. And if you've got Th2 type cells, you need a regulating cell that works against that. And one of the huge questions in immunology is how do these regulating cells actually turn off the other cells? That is really not known, although there's some of the information is that they produce extremely sort of toxic molecules, which one of them, which probably includes a thing called adenosine, which sort of just paralyses the cell. It doesn't kill it necessarily, but it just totally turns it off. It just sort of is like the light goes off. Anyway, so that's sort of part of how the immune system works. And the other thing I just wanted to talk about, just because this is the other way that the brain gets damaged, and then a lot of what we've been trying to do has been stop it, is that if you look at the axonal deterioration that occurs, after all, like the nervous system is sort of electrical with a wire, with cells on one end and cells on the other, and the electricity, which is actually sodium and potassium, has to get down. The electrons have to get from one end to the other. And there's all sorts of ways that this gets damaged. T cells themselves come in and do awful things to it. Macrophages come in and take the myelin away. And then there's all these other sort of chemicals that float around, nitric oxide, other reactive oxygen things, too much glutamate, metalloproteins and cytokines. And there's been treatments that have been tried against a whole host of these things. So there's been hundreds of actual immune-type drugs tried in MS. Many of them haven't worked terribly well, but fortunately some of them have. Now, if I just, I'll just come back to talking about the interferons. The interferons are, this is the 4 interferons, and they've all been tried early on in the disease. Interferons actually work to affect many of those components of the immune system. So not only the T cells and the B cells, but a lot of the cytokines that are produced. And exactly how interferons work in MS is not known. It was really tried originally because it was thought maybe it's a virus, and we'll try it because it does actually seem to work. The body produces it when we make viruses, but it's not clear that it's working as an antiviral. It's clear that it's doing many things to the immune system. But it just shows that very early on, it actually has quite a dramatic effect on the disease, and all of them have an effect on the disease. Now, one of the things that I was asked to talk about was cure, and we sort of would have to define a cure, because a cure could mean many different things. I mean, it could mean that nobody ever gets MS again, which is really prevention, or it could mean if you get it, but it's very early, you only ever have one attack and you never have another attack. Now, theoretically, if these people had one attack and it stopped many of them having a second attack for a long time, if we could have a treatment that stopped them having an attack for 40 or 50 or 60 years, that's actually, they're cured, I suppose. Like, if they don't have an attack till after they're dead, well, that's all right. Sort of thing. But so that's better than nothing. Now, then we need other cures as well. Like, could we make it work later so that even if people have had multiple attacks, can you still completely stop progression? And that's actually not probably really a cure, that's a management, and maybe what we mean by a cure for some people is if you do this for 3 days, then you'll never have to worry about it again. But I think that we haven't got anything like that. But we have some things that if you take them early and you're a very good responder, maybe it virtually will never be a huge problem. But not in everybody, because you can see that there's still 20% of people with Avanex, or 30%, or about 25% with benefit. Even at 2 years, some of those people have still converted to having MS. But at the 5-year point, with the benefit study, some people had still never had another episode. Anyway, now, the other thing that sort of got really not thought about to begin with was just, does this, because we've worried about, are treatments dangerous? Like, some of these treatments might be dangerous. This is a disease that actually doesn't alter people's life expectancy rapidly. So what happens long term? And the only long-term study that's been done is the Interferon long-term study, which is actually out to about 20 years, and they found everybody but 4 people. They were mostly in the US and Canada, and they chased them up, which included sort of private detectives and the CIA and the FBI. So they found everybody, and people very mobile in the US. Anyway, what they found is that if you had been on interferon in the original active treatment group, you were much less likely to die at 20 years later. So, of course, most people hadn't died, but it really did have an impact on that. So one of the conclusions is that beta-ferron does not cause death. It doesn't accelerate it. In fact, if anything, it substantially reduces it. Now, I just wanted to leave the conventional therapies now and then go on and just talk about Tysabri a little bit. Those graphs are the amount that Tysabri reduces the relapse rate on an annual basis, so by 68% each year. So on average, people have about a half or one relapse each year. It depends a little bit how often people get contacted, and because if you only see somebody every 2 years, mostly people only can remember, sort of the last year. Often if it's only just a few weeks, you put it out of your mind. But if you see people every 3 to 6 months, people's relapse rate is often about half to one a year. And it had a very substantial reduction in relapse rate. Now, this drug works by binding to the CD4 cell and the CD8 cell, but it binds the way it would get into the brain, so it can't get in. It is interesting that it actually binds the way the nasty effector cells would get in, But actually the way the T regulating cells get in, they don't use VLA4, they use another marker, and it might let them still get in. So that might be partly how it works. So I think that with some of these treatments, that wasn't known beforehand and now it is. So some of the ways that things are working, we are sort of still learning about, I suppose. I'll just talk briefly about fingolimod, which was derived from a mushroom, it is a mushroom, or a type of fungus, really. Many fungi, because to live, they have to sort of be able to survive on something that's like near it and also alive. They create things that kill other things. So that's like penicillin was a great fungus, cyclosporin comes from a fungus, and so does this drug. And it does some very interesting things. But it's got very similar looking graphs to cladribine. It's roughly equivalently active. So it's about a 50% reduction in relapse rate, and it was used even in people who are progressing so long as they have superimposed relapses. It targets a very funny sort of receptor that sits in all sorts of parts of the body, including the brain, and these receptors are called S1P receptors. And so when this drug is used in the short term, it has some side effects because it actually binds to some of them. So, for example, in the short term, it binds to the heart and makes the heart go a little bit slow, just for a little while. And it does some other things mildly to blood pressure. But it also keeps all the lymphocytes from getting out of the lymph nodes so they can't get into the brain. And that's at least the way it's thought to work at the moment. I think we'll find that it's working in extra ways, but it certainly seems to be fairly effective. It's also thought to be maybe not good in pregnancy, although there have been some babies born after fingolimod. And I just wanted to talk, these are just the other treatments that are being tested. So Campath is being tested at the moment. That's an antibody that was made in Cambridge pathology department. That's why it got called Campath. And it actually wipes out both B and T cells when you first give it. And then what happens is the bone marrow and the thymus make a whole lot of new cells, including quite a lot of regulating cells. And whether it's because you've got rid of all the bad cells or whether it's when the good cells come back, they're slightly different. But it seems to be very effective. And it has a 78% reduction in relapse rate compared to Rebif. So that's really very good. And you just take that for about you have 5 infusions the first year, 3 the second year, and then that's it for some time. There's some anti-B cell drugs that have been used. The original one was rituximab, and now they're making one that's a little bit more humanised, and it's being tested. But in the phase 2 studies, it also looks really quite effective. Both of those have quite a lot of... They have some toxicity, and they're associated with shingles or with some other immunosuppressed diseases, but mostly people who've been on it so far have found it helpful and haven't had too many problems. And the last one I want to talk about was bone marrow transplantation, and really to put it in the context of these other two. Bone marrow transplantation is sometimes talked about as the most severe form of sort of immunosuppression, but it's really not particularly different in some respects to some of these others. It also means that you destroy the B and the T cells, but this time you use chemotherapy. You can use radiotherapy as well. Depending on how much you do it, you can get your own to grow back, or you can have somebody else's. When you have somebody else's, it's extremely dangerous, really. There's a significant mortality rate. When you use your own, there's still a mortality rate, but it's not quite so... you don't need as much chemotherapy. But it's got all the side effects of the chemotherapy, and it hasn't been tested in near as carefully as the Campath and the rituximab. And it's not clear that it offers any particular advantages over those others. So I think that the reason that we're keen on early treatment is because you have normal brain when it starts, and it gradually, there is damage that occurs in it, and it's quite a lot of damage if the inflammation is not controlled. So I thought that in summary, I just want to say that the therapies we have so far are partially effective. The early ones are extremely safe. They do appear to work better early, not just that it's better to use them early, but they maybe work even better early. Early on in the disease, very significant damage occurs which destroys the spare capacity or the reserve, just like everybody's got sort of a kidney that you could donate and not know, that not harm you. You've got a lot of spare brain capacity, and if it gets destroyed, then it's very hard to get it back. And I think that progression occurs when this is exhausted. The newer therapies are very effective, but they have more risks. And how to sequence all of these therapies is stuff we're still working out. Thank you.